Off the coast of Vancouver Island, scientists just did something that's never been done before in the entire history of geology. They watched, in real time, as a piece of the Earth's crust tore itself apart. Not reconstructed years later from old rock samples, not modeled on a computer, actually imaged mid-collapse using sound waves bounced off the seafloor like a planet-sized ultrasound. And what that image revealed was a tectonic plate sitting directly beneath one of the most dangerous earthquake zones in North America, actively fracturing into pieces. This isn't speculation, and it isn't an exaggerated headline stretched from a vague, unrelated finding. This is a real peer-reviewed study published in the journal Science Advances, led by geophysicist Brandon Shuck, now an assistant professor at Louisiana State University, conducted while he was a postdoctoral researcher at Columbia University's Lamont Doherty Earth Observatory. And the location where this tear is happening isn't some obscure, disconnected patch of ocean floor. It's the northern end of the Cascadia subduction zone, the exact same 700-mile fault system that runs along the Pacific Northwest coast past Vancouver, past Seattle, past Portland, all the way down to Northern California, and the same fault system capable of producing a magnitude 9 earthquake. Picture what that actually means for a second, because it's easy to let the technical language slide past without registering the strangeness of it. Somewhere beneath thousands of feet of dark, cold ocean water, a piece of solid rock the size of a small country has been slowly, silently coming apart. Not in some ancient, long-finished chapter of Earth's history, but right now, in a process, scientists have finally managed to catch mid-motion, using instruments precise enough to hear the planet's own crust groaning under the strain. This is the kind of thing that usually only shows up in geology textbooks as something that happened millions of years ago, explained after the fact from cold, static evidence. This time, it's happening in the present tense, and researchers have a front row seat to it. Here's what the researchers actually found and why it matters. Off the northern tip of Vancouver Island, 3 tectonic plates come together in a genuinely chaotic geological neighborhood. The Juan de Fuca plate, the Explorer plate, and the Pacific plate, all grinding against each other and against the North American plate in different directions, at different speeds, using a research vessel equipped with seismic imaging technology, essentially firing sound waves down through miles of ocean and rock, then reading how those waves bounce back to build a detailed picture of what's happening far below the seafloor. Shuck's team captured something no one had ever clearly seen before. An active fault slicing directly through the descending Juan de Fuca and Explorer plates, with one section of the slab having already dropped by roughly 5 kilometers, about 3 miles, relative to the section right next to it. To understand why that's such a big deal, you first need to understand what a subduction zone actually is, because it's the single most important piece of context for everything else in this story. A subduction zone forms wherever one of Earth's tectonic plates, massive rigid slabs of rock that make up the planet's outer shell, collides with another plate and gets forced underneath it, sinking down into the mantle. This isn't a gentle process. Subduction zones are responsible for some of the most powerful, destructive events our planet produces. The largest earthquakes ever recorded, explosive volcanic eruptions, and the slow, continuous recycling of old ocean floor back into the deep earth. The Cascadia subduction zone, specifically, is where the Juan de Fuca plate, moving eastward at roughly 4 centimeters a year, dives beneath the much larger North American plate. That grinding, locked collision has been building stress for centuries, and it's the exact mechanism behind the region's greatest long-term danger. A full margin rupture capable of producing a magnitude 8 or 9 earthquake, along with a tsunami that could reach the coast in a matter of minutes, faster than many communities could realistically evacuate. The last time Cascadia produced a rupture like that was in January of 1700, a genuinely massive earthquake, so powerful that the resulting tsunami crossed the entire Pacific Ocean and was documented, without explanation at the time, in written records in Japan. Since then, the fault has simply been locked, quietly accumulating strain, waiting. Canadian and American geological surveys, studying sediment evidence buried along the coastline, estimate that earthquakes of this scale strike the region roughly every 300 to 800 years. A wide window, but one that places the current moment, 326 years after the last rupture, well within the range of geological possibility for the next one. So when a team of scientists announces they've directly observed a tectonic plate tearing apart in this exact region, it's completely reasonable for that news to land with some real weight. But here's where the honest, careful version of this story actually diverges from the more sensational one. And it's worth understanding the distinction clearly because it changes what this discovery actually means for anyone living along that coastline. The Shuck's team observed isn't happening on the main, locked interface between the Juan de Fuca plate and the North American plate, the specific surface where stress has been building since 1700, and the surface that would actually rupture in a future megathrust earthquake. It's happening deeper and further north, specifically within the subducting plate itself, at the boundary where the Juan de Fuca and Explorer plates meet a structure called the Nootka Fault Zone. What the researchers are actually documenting is something different, and in its own way more fundamental. The process by which an entire subduction zone, over the span of millions of years, eventually shuts itself down. Subduction zones, it turns out, don't last forever, and geologists have wondered for decades exactly how they finally come to an end. Brandon Shuck offered a genuinely useful way to picture the mechanism at play. Getting a subduction zone started, he explained, is like trying to push a train uphill. It takes an enormous amount of force to get that heavy, dense oceanic plate to begin sinking beneath a neighboring plate in the first place. But once it's moving, once that slab is actively sinking under its own weight, it becomes almost unstoppable, like a train racing downhill. Ending that process requires something dramatic. In Shuck's own words, essentially a train wreck. What his team caught, for the first time with this level of clarity, is exactly that. A subduction zone in the act of derailing, not all at once, but piece by piece, as fragments of the sinking plate tear away and detach from the section still actively subducting. The imaging revealed multiple large faults slicing through the descending plate, including one dramatic break where the slab has dropped by that roughly 3-mile margin relative to its neighboring section. Along one particularly significant fracture, stretching about 47 miles, the researchers found something else worth understanding: an uneven pattern of small earthquakes, with some sections producing regular detectable seismic activity, while neighboring sections along the very same fault stayed unusually, tellingly quiet. The quiet isn't an absence of activity, it's evidence of something more specific. Shuck explained that those silent stretches mark places where a piece of the plate has already fully broken away and detached. Once a fragment has completely separated, it no longer generates the friction and strain that produces earthquakes along that particular boundary, because it's no longer actively grinding against anything. The quiet zones, in other words, are the parts of the plate that have already finished tearing. The active zones are where the tearing is still happening right now. This piece-by-piece process is what researchers call segmented or episodic termination, rather than an entire subduction zone shutting down all at once in one single catastrophic event. It fails in stages, with individual fragments detaching over time as the larger system gradually loses the force that was pulling it downward in the first place. As those fragments break away, the remaining, still connected portion of the plate loses momentum piece by piece, until eventually, over a timescale of millions of years, the entire system grinds to a halt. That process, according to the research team, has a direct, tangible geographic consequence worth understanding, because it's specific and measurable, not just an abstract concept. Once the Explorer plate segment is fully captured and absorbed by the larger Pacific plate, a process already underway based on the tear currently being observed, the researchers project that the active Cascadia subduction margin will effectively shrink by about 47 miles from its northern end. The nearby triple junction, where multiple plate boundaries currently meet and grind against each other, would likely shift position as a result, and the corridor that currently functions as a complex, messy shear zone would simplify into a more straightforward transform boundary, similar in character to a strike slip fault like California's San Andreas, where plates slide horizontally past each other, rather than one diving beneath the other. Here's the detail that matters most for anyone trying to honestly understand what this discovery means for earthquake risk along the Pacific Northwest coast, and it's a detail the research team themselves has been consistently direct about. In study after study, interview after interview, this finding does not significantly change the hazard outlook for the broader Cascadia megathrust. Suzanne Carbat, a co-author on the research from Lamont Doherty, put it plainly: scientists have known for decades that subduction can stall when a buoyant, less dense section of an oceanic plate arrives at the boundary and resists being pulled down. What's genuinely new here isn't the existence of that process, it's the clarity. Researchers haven't previously had this detailed, this direct picture of a subduction zone actually caught in the act, rather than reconstructed after the fact, from indirect evidence. That distinction is worth sitting with because it's the difference between a genuinely fascinating scientific discovery and an inaccurate, fear-driven headline. The tear being observed isn't a new crack suddenly opening up beneath the Pacific Northwest, threatening to trigger an imminent earthquake. It's scientists finally getting a clear enough look at a process that's actually been unfolding, gradually, over a timescale of millions of years. A process responsible for shaping ancient plate fragments still found today off the coast of Baja California, remnants of a similar, long-since-completed termination of the ancient Farallon plate system. What's happening off Vancouver Island right now may be a live, ongoing example of exactly the kind of gradual dismantling that produced those ancient fragments in the first place. It's worth being honest, too, about a more specific, more debated angle that's emerged in some of the coverage following this research, because it deserves careful, measured treatment rather than either dismissal or amplification. Some analysis building on this work has pointed to GPS measurements showing the Explorer plate's convergence rate slowing to roughly 2 centimeters per year, less than half the 4 centimeter rate of the neighboring Juan de Fuca plate. The reasoning goes that as the Explorer segment's own downward pull weakens, some of that gravitational force, the slab pull that drives subduction, could be transferring onto the Juan de Fuca plate instead, potentially accelerating stress loading on the portion of the locked megathrust immediately to the south. This is a genuinely interesting hypothesis, grounded in real, measurable data about differing plate velocities. But it's important to be clear that this specific interpretation, connecting the Explorer tear directly to accelerated stress buildup on the main locked interface, is a more speculative extension of the core published research, not something the original study's own authors have made as a central, confirmed claim. The core, peer-reviewed finding is about how subduction zones terminate over geological time. Whether that specific process meaningfully accelerates the timeline toward the next major Cascadia earthquake remains a genuinely open, actively studied question, not a settled one. There's a related piece of research worth mentioning here too, because it reinforces just how much more complex this entire coastal fault system has turned out to be than earlier models assumed. Further south, at the Mendocino Triple Junction off the coast of Northern California, a separate point where 3 tectonic plates meet, a different research team recently discovered that the junction isn't simply made of 3 plates as long assumed, but effectively 5 separate moving pieces, including a previously unconfirmed fragment called the Pioneer Fragment, a chunk of older rock being dragged down alongside the Gorda Plate. That finding, using a technique that involved analyzing thousands of small, low-frequency earthquakes invisible to anyone at the surface, is a reminder that the entire Pacific Northwest and Northern California coastal fault system is proving to be far more intricate, layered, and segmented than the simplified textbook picture most people grew up with. Not because the underlying danger has changed, but because scientists are only now developing the tools sensitive enough to actually see it clearly. What can be said with real confidence, based on the actual published science, is this. Earthquakes along the Cascadia subduction zone remain a serious, well-documented, ongoing risk, entirely independent of this new tearing discovery. Scientists estimate the fault is capable of producing earthquakes in the magnitude 8 to 9 range, events that release energy built up over centuries and that could trigger a tsunami reaching the coast within minutes of the initial rupture. That risk existed before this research was published, and it exists at essentially the same level after it. What this new discovery actually adds isn't a fresh additional threat. It's a sharper, more detailed map of exactly which parts of the deep tectonic system are actively fragmenting, how the plates bend and shift as that fragmentation continues, and where stress tends to concentrate as a result. That refined picture genuinely does matter for scientists building more accurate models of how a future Cascadia rupture might actually unfold, potentially threading through a more segmented, more complex slab system than earlier, simpler models assumed. It sharpens the science. It doesn't raise the alarm. There's also a genuinely fascinating secondary layer to this discovery worth understanding, beyond the earthquake risk conversation entirely. Plate tears, like the one being observed off Vancouver Island, don't just matter for seismic hazard modeling. They can directly shape the seafloor environment above them in ways that ripple outward into the broader ecosystem. Researchers have noted that these kinds of tears can influence where warm fluids and methane seep upward through the ocean floor, creating small, localized pockets of marine habitat that depend specifically on that geologic activity. In that sense, the same tectonic forces responsible for the region's greatest long-term earthquake danger are also, in a much smaller, much more immediate way, actively shaping small corners of marine life on the seafloor today. There's something worth sitting with in that last point, separate from any earthquake risk conversation entirely. Most people go their whole lives thinking of the ground beneath them as fixed, permanent, the one truly stable thing in an otherwise unpredictable world. What this research actually captures is a quiet reminder that nothing about Earth's crust is really permanent at all. It's just moving on a timescale so much slower than a human life that it reads as stillness. Continents drift, oceans open and close. Entire subduction systems, responsible for building mountain ranges and triggering the planet's most powerful earthquakes, eventually run out of momentum and grind to a halt, replaced by whatever tectonic arrangement comes next. Catching one of those systems in the act of that slow-motion ending isn't a warning sign. It's a genuinely rare glimpse at the planet doing what it's always done, just usually too slowly and too far out of sight for anyone to actually watch it happen. So where does the honest version of this story actually land? Scientists have genuinely, for the first time, directly observed a subduction zone in the act of breaking apart. a real, confirmed, peer-reviewed finding published in one of the field's most respected journals, led by a credible team of researchers using solid, verifiable seismic imaging methodology. That discovery is happening specifically off the northern coast of Vancouver Island, within the same broader Cascadia system that runs the length of the Pacific Northwest coastline, and it does represent something genuinely new in geological science. The clearest picture ever captured of exactly how these massive systems eventually shut down piece by piece over millions of years, rather than all at once. What it is not, based on the research itself and the direct statements of the scientists who conducted it, is confirmation that the long-anticipated Cascadia megathrust earthquake has become meaningfully more imminent, or that this specific tear represents some kind of new additional threat layered on top of the region's already well-understood seismic risk. The fault is getting a clearer map drawn of it. It isn't, according to the people who actually did the research, getting more dangerous in any way that changes what residents along that coastline should be doing right now, which remains exactly what earthquake preparedness experts in the region have been recommending for years, regardless of this discovery. Sturdy, updated building codes, clear coastal evacuation routes, and a genuine practiced emergency plan. Because the big one, whenever it eventually comes, was always going to be a real event worth preparing for, whether or not this specific fragment of ocean floor happened to be caught for the first time in the act of quietly tearing itself apart.